each webinar. Registration is now open for the December 14th webinar. So let's get started. If you have questions for the speakers, you can drop those in the Q&A or the chat feature on the Zoom link. You can go ahead and type your questions into the chat or Q&A, and either myself or Miranda will share those with the presenters. So let's go ahead and get started with our first speaker, which is Dr. Matthew Fidelibus, who works for the University of California Cooperative Extension, based out of Parlier, California at the UC Kearney Ag Center. He's a viticulture specialist, and today he will be presenting on nitrogen in table grapes, assimilation, distribution, fertilizer recovery, efficiency, and monitoring. So Matthew, if you can share your screen.
Okay, I will here. Okay, you guys see my screen now?
Yes.
All right, great. So what I'm going to talk about in this presentation is how does N affect annual growth of leaves, stems, fruit, and how much N is needed to support that growth. I'll also talk about nitrogen effects on fruit quality and yield, tissue sampling to monitor vine N status, how fertilizer application strategies affect fertilizer use efficiency, briefly list some non-fertilizer sources of N that you should consider, and then touch on how this information can be used to develop a nitrogen management plan. And then I also want to mention some ongoing research that we're doing to develop tools to further assist growers in developing and assessing nutrient management plans. So first, we'll talk about nitrogen and the annual growth of the vines, and specifically how much N do vines allocate to the annual organs, which include the leaves, the stems, and the fruit. So I'm going to give 2 examples from a vineyard that had a low background N status when we started the study. And we'll talk about that first. And then I'll show you some slides of similar data from a vineyard that had a high N status when we started the study. So this low N vineyard is a flame seedless table grape vineyard. Here's a picture of it on the same slide here. And it was planted on Freedom rootstock in 2012. And it's a deep sandy soil with low organic matter. There's low nitrates in their irrigation water. And the unfertilized vines, when we started the study, had very low petiole nitrate, and basically from about 5 to 250 ppm at bloom. And the vigor was low to moderate. So what we did was we applied fertilizer at 3 different rates, either none or about 36 pounds or 90 pounds per acre, the equivalent of that, and looked at how it affected N uptake, biomass, fruit yield, and quality. So first, just looking at the overall growth in this vineyard, as you might imagine, which had low N status, the fertilization did increase dry matter accumulation. So here you can see we look at leaves, stems, and fruit. These are grams of dry matter per vine, and then the total annual growth. And supplying extra N when N was missing did increase leaf biomass, also stems, and at the highest rate, it also increased fruit. So overall, there was a total annual growth increase there with more nitrogen. And in this vineyard, it actually took the highest rate of N in order to increase all of these parameters. We also took this information and developed a nitrogen budget for these vines. So this table shows you the annual application rate in pounds per acre of nitrogen, either 0, 36, or 90. And then we have the total N accumulated by harvest in pounds per acre in the leaves, stems, fruit, or the annual growth. And fertilizer increased vine growth and N content of the vines. But the fertilized vines partition a similar amount of N to the leaves. So if they got some fertilizer, they seem to allocate about 40 to 43 pounds of N in the leaves. Vines receiving the highest rate of N partition more N to stems and fruits than the other vines. And that's due to increased growth and also higher N content in those tissues. And these results were consistent for 5 years. Now, if you're monitoring vine N status, you're probably going to be looking at TN either in blades or in petioles. Here, I want to show you some data from blades. And you can see the effects of fertilizing on TN and TK. So we measured potassium also, since that's another macronutrient that's very important to the vines, although we didn't adjust the potassium fertilization in this vineyard, only nitrogen. So the grower was applying potassium, and we did not do anything differently in any of the vines from what the grower was applying. So N fertilizers increased leaf TN throughout the season. So you can see in this table, we have main effects of year. That's that first batch of data near the top of the table. Then we have the effects of fertilizer amount. And then I haven't talked about it yet, but we also looked at the effect of split applications. So split applications, we tested 2 different split applications, either one where the amount of N that was applied over the course of the year was applied in 2 split applications, so half at each time, or over 10 split applications, so 1/10 at each time. And we look at the first 2 sets of data are TN and TK for bloom, and then we have veraison and harvest. And what we found is that if you applied, well, the split applications, I should say, were applied, the first split went down a month after bud break, and the remainder was after fruit set. And the 10 split applications started a month after bud break, and they continued every 2 weeks until they were all applied. And what we saw was in the beginning of the season, if the N was applied in a slug, which this 2 split applications, we saw N increased early in the season, whereas if it was applied over the 10 split applications, we saw it increase N later in the season. So you can see, for example, at bloom, the 2 split applications increased TN more than the 10 because more N had been applied by bloom. But as we get toward the end of the season, where we're parceling out the N over a long time, but a little bit over a long period, that was better at increasing N toward the end of the season as compared to the slug. And the quantity of N also affected TN. You can see that if they were unfertilized, they had about 2.5% nitrogen at bloom, whereas if they got the highest rate of N, they had about 3% nitrogen at bloom. And that'll be important later when I show you some information on fruit quality. And the other thing I wanted to tell you about from this slide is that when you adjust the rate of a certain fertilizer, you can sometimes affect the nutrient content of something else. So in this case, we adjusted the rate of N that the vines were receiving, and we affected the potassium concentration in the leaves. So that's probably at least partly the effect of growth dilution. The vines that were given N had bigger leaves, and they had probably about the same amount of K, and so the K concentration decreased. So what about on fruit quality? This table here again shows the effects of different fertilizer rates and split applications on different aspects of fruit quality: weight, length, diameter, Brix, pH, TA, and these color data. But what I really want to focus on, and the main significant effects, I think, are on fruit weight. So in this N deficient vineyard, when we gave it more fertilizer, the berries were bigger, they were heavier, and they were longer and also wider. So that was the main benefit that we saw in fertilizing in this vineyard, was bigger berries. And so we keyed in on this fertilizer effect on berry weight to see if we could develop a critical value of N for this flame seedless vineyard. And so this chart is showing you berry weight increasing from about 2.5 to 6 grams on the vertical axis, And then on the horizontal axis, you see bloom time, leaf blade, total N. And you can see that in this vineyard, as bloom time, leaf total N increased, so did berry weight at harvest. And it looks like around 3% TN at bloom was sufficient to maximize berry weight in this vineyard. And if you recall from a few slides ago, when I showed you the effect of fertilizer rate on leaf blade TN, the only rate that raised average leaf blade TN at bloom to 3% or higher was the 90-pound rate. So if the vines are deficient in N, they actually need more N in order to raise their tissue N content and also optimize fruit quality and yield. So we saw that in productivity here as well. So this is from that same vineyard again. And you can see the effect of fertilizer rate, which is this middle section of the table here on annual harvest. The highest rate of N increased the harvest weight from the fruit or from the vines. And that was probably largely because of the effect on berry size. So we increased berry size. They ended up harvesting more fruit. And that was the big effect of nitrogen in this vineyard. So how about a situation where the vines already have a high N status? You might recall from that other vineyard, those vines, if we didn't fertilize them, had barely any nitrate in their petioles at bloom. What about a vineyard that does have a lot of nitrates? So here's a different vineyard, a different location, different grower. And you can see this table here shows you effects of fertilizer timing. It's a similar experiment, 2 applications versus 10. And the amount of fertilizer in the columns here, 0, 1x, that's the amount of N that we estimated was removed by picking the fruit the previous year. So we used an estimate of 3 pounds of N per ton of fruit. And we looked at the grower's harvest data, and that's how we came up with this rate. And 2.5x was 2.5 times the replacement amount of N. And these data here are the parts per million nitrate, nitrogen in petioles at bloom. And you can see even in the unfertilized vines, they're over 2,000 ppm. That's certainly in the sufficient, if not excess range. And but even so, if we increase the rate of nitrogen, we were able to increase the nitrogen levels in petioles at bloom. So they do respond to the fertilizer applications, but what is the practical implication? So here we have the total grams of N per vine in response to fertilizer amount and split applications at different times. So bloom is this top table, then we have veraison, and then we have harvest. And you can see that fertilization of vines that already had a high N status, it increased the amount of N in the vines at bloom. So here, this top section is the amount of nitrogen in the vines at bloom. And you can see that going from, I thought I could draw on this. Going from 0 to the replacement amount to an excess amount, we did increase the total amount of nitrogen, at least once we started fertilizing at bloom. But once we got into veraison, which is this table here, or harvest, applying more fertilizer didn't increase the amount of N in the vines. So only in the early part of the season did we see that effect. Now we look at fruit quality. And in this vineyard, fertilizing had little effect on fruit quality in this high N status vineyard. So we look at whether we looked at weight, length, diameter, firmness, Brix, pH, TA, or these color variables. In this flame seed, this vineyard where the petioles are already 2,000 ppms nitrate at bloom, we didn't see any benefit of giving more fertilizer in terms of fruit quality. And we also did not see any benefit in the high-end vineyard of fertilization in terms of yield. So we didn't see any effects on fruit quality. We also didn't see any effects on yield. So we looked at every time the grower harvested with a commercial crew, we were out there weighing what they were harvesting and also weighing what they culled. And we didn't see any effects in general on pretty much all the variables we measured. We collected similar data in another high end status vineyard, this time Crimson Seedless. And the story is pretty similar to Flame Seedless. There is no benefit of fertilizing with respect to fruit size or most aspects of fruit composition. We did see some changes in berry color related to fertilization rate. So this variable here, H, that's the hue of the fruit. And a low hue angle, for example, a hue angle of 0 would be perfectly red. And as the hue angle starts to increase, it becomes more yellow colored. And so this lower hue angle for the unfertilized fruit of 20 is actually more red than the fruit that were given some fertilizer, either the replacement rate or the high rate. So in this vineyard, which also had a high end status, giving the fruit more nitrogen actually reduced the color. And those fruit quality data were collected right before the first harvest. So let's see what effect that may have had on harvest data. These data were again collected with the help of the grower. The grower's crew went and picked according to their standard picking criteria. And what we saw was they actually picked less fruit from the fertilized vines than they did from the unfertilized vines on the first harvest. And I think that's because the fruit was less red colored than when it had been fertilized than it was when it hadn't been fertilized. And but over the course of the season, there was enough variability in picking after that, that by the end of the season, we didn't actually see any difference in yield related to fertilization. So it was just in the timing of picking, being that the picking was delayed in the fertilized vines as compared to the non-fertilized vines in a vineyard that already had high end status. And here are some data just to show you a range of the N in different vineyards with different varieties. It ranged anywhere from a low of about 134 pounds of N per acre in the annual growth of the vines to a high of over 200 pounds in one vineyard. This was in an Autumn King vineyard, a late harvested variety that also had very high yields and it accumulated more nitrogen. And this low one was in an early ripening variety that had a lower nitrogen status. Here's a nitrogen budget for a vineyard we were working in, Valley Pearl Vineyard in Shafter. The total N grams per vine in leaves, stems, and fruits, and the equivalent total N in pounds per acre in these same organs, leaves, stems, and fruit, and the annual growth. And we estimated that about 40% of the N would be in the fruit in this vineyard, and we were very close. So in summary, the vines allocate anywhere between 50 was in this extremely N deficient vineyard where the vines weren't fertilized, and 200 pounds of N per acre in their annual growth. The amount of N in the annual growth depends on vine size and N content. And about 40% of the N in the annual growth is in the fruit. The remainder is in the leaves and stems. N deficiency limits berry size, and it can also affect berry chemistry and color. And applying more N than needed, though, does not further improve fruit quality and it may delay maturity. So it's important to monitor your vine N status because you really don't need to fertilize some vines and other vines you do. So right now, the standard method is analysis of tissue samples. Petioles are a standard tissue in California, but some people do prefer blades. The mineral content of plant tissues can change rapidly over the course of the season, especially around bloom, and that's why we choose certain phenological dates as standard timings for collecting these tissues. That way you can compare your data from year to year and really get a feel for how your nutrition plan is affecting vine end status. And so those standard sampling times are bloom and veraison, but those results are usually correlated. So if you look at the results from bloom and compare them to veraison, you often see a good correlation. Still, it's helpful to choose samples at both those times, because if you take a bloom sample and it indicates that you need to fertilize, you have another opportunity to compare, to fertilize and then compare your end status at veraison. Okay, so these are typical critical end values at bloom for nitrate, nitrogen, and petioles. You can see that one flame seedless vineyard I was talking about that had a high end status, over 2,000 ppm. And so it was in the excessive range. And so not really surprising that not fertilizing didn't have any effect on fruit quality or yield. And fertilizing, even though it did increase tissue and content, it didn't really improve, it did not improve fruit quality or yield. So some people ask whether they should look at total N or they should look at petiole nitrate. And we compared petiole total N, which is this vertical axis, to petiole nitrate N on this horizontal axis for several different table grape varieties, and found in general they're pretty well correlated. We also looked at total N of petioles and total N of leaf blades, and we found that they were also usually linearly correlated. So in the previous data set, I'm just showing you total N of petioles versus nitrate N of petioles, and you can see they're correlated. Here, I'm showing you total N of leaf blades on the vertical axis and total N of petioles on the horizontal axis. And in most years, they're they're linearly correlated, and they show a similar correlation from year to year. But in this one vineyard, or in this one year, 2019, we got some higher values of total N in the petioles than we had previously, and we see a bit of a plateau there. So it seems like at these more moderate or lower levels, there's a good linear correlation between TN of leaf blades and TN of petioles, but maybe the relationship might change at high N levels. Well, so since petioles, one of the reasons why we did this comparison of total N and petioles versus total N of leaf blades is because a lot of people collect data from petioles, and fewer people, I think, collect data from leaf blades. But we wanted to explore the possibility of using remote sensing as an end monitoring method. And if that were to be successful, then we wanted to be able to give growers some indication of what total N measured this way might mean if they have been collecting petioles in the past. So we wanted to first see what the relationship was between petioles and leaf blades. It looks like in most cases, they're very well correlated. Well, now what we're doing is we are working with Ali Pereza, who is a extension specialist in agricultural and biological engineering at Davis. He is doing some imaging of vineyards that we're working in with a drone and looking at, so he is collecting this reflectance data with the drone, reflectance of the wavelengths being reflected off the leaves from sunlight. And then we're out there collecting tissue samples from the same leaves that he's imaging. And he's feeding these tissue sample data into some algorithms with the reflectance data, and actually using artificial intelligence to try to develop good algorithms that can predict the nutrient content of grapevine leaves on individual vines, and generate a map of a vineyard that shows you zones of sufficiency in the vineyard. So here is an example of a vineyard that we are working in. We ground truth these data for many of these vines, and then a map was developed based on the algorithm, what was comparing the multispectral imaging from data from the drone versus the ground truth end content. and he developed this map of the vineyard. So a grower could use this kind of a map either to better select areas for sampling for their traditional sampling scheme, or maybe if we can improve this, these algorithms even more, perhaps at some point in the future, we could just use imaging and not need to collect tissue samples to go to the lab. So that's our idea. Besides lab results, it's always good to do a visual inspection. And here is one of our panelists, Mark Battany, in this picture. And the reason why I put this picture in here is because this picture was taken in a vineyard in Argentina where the grower was collecting tissue samples and sending them to a lab in Chile for analysis. And the lab was then giving him recommendations on fertilizing, and the grower is implementing those recommendations. So the grower told us that the lab was recommending that he fertilize in this vineyard, and so he was. But you could just look at this vineyard and see that it does not need, certainly doesn't need any nitrogen. This canopy is very thick. The picture is taken, I think, in the middle of the day, and you can still see how dark it is in there. And not only is the canopy very thick, but there's also a very thick layer of shed leaves that coat the bottom of the vineyard, so the vineyard floor. So you need to do some due diligence, go out there in your vineyard, take a look at it, make sure that the results from the lab agree with what you're seeing before you commit to using that information. So here's a picture showing low nitrogen vines. This is one of our studies. These vines have not been fertilized in 5 years. They have very pale colored foliage. The canopy is very sparse. I don't know if you can see it very well on your monitors, but the berries are irregular in size and small compared to vines here on the other side that got a high rate of N, 90 pounds per acre. These got no nitrogen per acre. This canopy is much thicker, and the berries are much larger and more uniform in size. And the leaves are different color. Here's a different view of the same vines. The low end leaves are smaller. The high end leaves are larger. They also vary in color. Okay, so
Matthew,
I think
we
I have
have
a few more minutes, even though it's half past. Is that right?
Yeah, we have about five minutes.
5 minutes. Okay. So we talked about, the effects of nitrogen, and we talked about how you don't need to apply if you already have high nitrogen. You need to apply if you have low. What about when are you going to apply? So I was just talking about this to some growers in Lodi. I was invited to give a talk on kind of shutting down a vineyard. So a lot of people think that maybe they should apply nitrogen at the end of the season. And what I want to show from this slide is this happens to be in Grenache vineyard. REN is recovery efficiency of nitrogen. These are different years where the data were collected, 2017, 2018, or 2017 and 2018. And you can see that, okay, plus N is a split application in the spring. Plus N pH is nitrogen at the end of the season. And look at recovery efficiency. It's very low for nitrogen applied at the end of the season being post-harvest. It's much higher when it's applied in the spring. Here's another set of data, this time from Rafosco. Recovery efficiency was, again, much higher for nitrogen applied in the spring than it was for nitrogen applied after harvest. So why would it be that the efficiency is so low when it's applied post-harvest? Well, this shows you the total grams of nitrogen per vine at different times. So 9.5 is the harvest date. EOS is end of season. And you can see at harvest, there's about 30 grams of nitrogen in the leaves. But at the end of the season, so these are fallen leaves, basically how much nitrogen was left in the leaves when they fell off the vine, only 15 grams. So about 14 grams of nitrogen was taken out of the leaves during senescence. And let's look at trunk and roots. This is where your reserves of nitrogen are accumulating. Well, they had the opposite trend. They increased in the case of trunks, from 7 grams to 11 from harvest to end of season, and in roots from almost 20 to about 30. And the total increase was 4 grams in trunk, about 13 in roots. And so you can see that about 85% of the increase in N in the trunk and the roots could be accounted for by the decrease of N in the leaves. So a lot of the N that accumulates in the vine after harvest can come from the leaves. Okay, running out of time here, so I just want to talk about some non-fertilizer sources of N. Water can be a very significant non-fertilizer source of N. These are just different vineyards that we happen to work in, and we took water samples, and we also measured how much water was applied. And the bottom line is that these vineyards were receiving anywhere from 13 to 35 pounds of N per acre just in nitrate that was in the irrigation water. So certainly take that into account. So how can you use this information? I think you should annually monitor and record your yields, your tissue, either petiole or blade test results, and nitrates in the water. If growth and tissue test results are high, and fertilization may not be necessary for 1 or more seasons, especially if non-fertilizer sources of N are available and substantial. So in that case, just monitor. If yields, growth, and tissue tests are normal and sufficient, plan to replace N in the fruit using 3 pounds of N per ton of fruit removed from a vineyard. And you should include all the fruit removed, not just maybe what's packaged, for example, as table grapes, but any other fruit that might come out of the vineyard going to the winery or whatever. If yields and growth are low and tissue test results are borderline or low, consider replacing more than the amount of N in the fruit, up to 2 times that estimated N in fruit, accounting for other sources of N in the vineyard. And to maximize recovery efficiency, apply N in the spring, avoiding bloom. I would bracket bloom basically, and use split applications, especially if high rates of N are required. So I want to acknowledge the California Table Grape Commission for sponsoring this research, and Larry Williams, who helped me collect most of this data and collected also the wine grape data that I shared with you. Okay, that concludes my presentation. Thank you for your attention.
Okay, Matthew, we've got a couple questions, but I'm going to go ahead and I'm going to let you answer one online, and then I'm going to ask you this question for the audience. This will be the second question. Does the nutrient content level from remote sensing vary based on variety, or is it fairly standard between vineyards?
That is a good and essential question, and we are determining that at the moment. So I don't have an answer that I can share with you, but we realize that this needs to work for different varieties and different vineyards if it's going to have value. And so we are testing this technology in different varieties with different vineyards right at the moment, but I don't have results I can share with you yet.
Okay, so, and then there's another question, but if you can maybe, if you can see that, maybe type an answer in there. It's focused on leaf tissue versus petioles. If you can write an answer, that'd be great. Just to follow up on that one question, Matthew, have you guys, the vineyards that you're using, have you thought about maybe using vineyards that have the same variety but different rootstocks and do remote sensing to see if there's value in or differences in the different rootstocks?
Yes, but not in a very systematic way, because then we would need probably at least 3 different vineyards of the same variety on a certain rootstock and 3 other vineyards in a different. So we have worked in different vineyards with the same variety but different rootstocks, but it's hard to know if differences that we see are strictly a rootstock effect. So for example, the very, very high end vineyard that we were looking at in Flame Seedless happened to be on 1103P, whereas the low end vineyard that we were looking at of Flame Seedless was on Freedom. But there are other differences between those 2 vineyards.
Sure.
One had much higher nitrate levels in the water than the other. One had a different soil type than the other. So it's hard to know what is strictly a rootstock effect versus what is a cyan effect.
Right. Okay. So some additional research that needs to be conducted. Matthew, thank you for presenting today. We appreciate you joining us. We're going to continue on with our program. Our next speaker is Mark Battany, who works for the University of California Cooperative Extension as a water management and biometeorology advisor out of San Luis Obispo and Santa Barbara counties. So Mark, if you can go ahead and share your screen. He will be talking about using satellite data to aid in irrigation management.
Okay. Yeah, thank you, Steve.
And we can
Okay.
see the slide.
Can you see that okay?
Yes.
Okay. Well, thank you very much. Yeah, so using satellite data to aid irrigation management. So just some background on our satellites. Landsat 7 and 8 are the American satellites that are currently being used. Landsat 9 was launched recently. Each one of these satellites takes 16 days to cover the globe, and they're staggered, so one passes over every 8 days. They're NDVI pixel size, 30 meters by 30 meters, and they also take thermal measurement, 100 meters by 100 meters. Landsat 7 was launched in 1999, and Landsat 8 launched in 2013. So I mentioned Landsat 9 was launched recently. It's now being calibrated, and it will be available then probably early next year for use and essentially replace Landsat 7. Okay, the Sentinel satellites, 2A and 2B, these are from the European Space Agency. They go a little faster, 10 days to cover the globe, and they pass over then once every 5 days because they're staggered as well. The nice thing about these satellites, they have a smaller NDVI pixel size, so 10 meter by 10 meter, but they don't have the thermal measurement. And I'll give you some examples of how that pixel size is important for us. These are more recent satellites. Sentinel-2A was launched in 2015 and 2B in 2017. So we have data available for these satellites back to these dates. Okay. So this slide demonstrates the difference in the pixel sizes between the Landsat on the left, 30 meter by 30 meter, and the Sentinel on the right, 10 meter by 10 meter. So the satellites, when they pass over, what they are measuring is this the square grid that you see in the kind of green and tan color. In the websites where we look at this data, it's overlain on top of an aerial image, but the satellite is not collecting that image with each pass. So that's something just important to keep in mind, is that you're looking at this over an older image, maybe taken by either satellite or airplane or something. So it's these square values that are of interest to us. That's the data that we're getting from the NDVI. So look how coarse the example on the left is with those 30 meter by 30 meter pixel sizes. So each one of those squares is given a single value by the satellite measurement. So if that pixel overlaps both vineyard block and a dirt road, for example, that value is an average of that condition. So it's important to understand that if we are using, for example, the Landsat data, that we need to keep sort of a border between the measurement area that's of interest to us and surrounding dry roads or dry fields, for example. The image on the right shows the advantage then of the much finer pixel from the Sentinel satellites, that 10 meter by 10 meter, and you can see that edge effect is much reduced. So just from using this as a visual analysis tool, the smaller pixel sizes really give us a much better advantage to understand patterns within the field. So that is a big advantage of the smaller pixel sizes. Now the Landsat satellites take a thermal measurement as well. Basically, a thing that has a measure of the temperature of the land surface, which can then be used in models to predict how much evapotranspiration is occurring. Those are taken on even larger pixels. So I've just sort of drawn a representation of what those 100 meter by 100 meter pixels would be. And you can, I think, get a feel now for how challenging it is with this large pixel measurement. When you have a single value to each one of those squares, which is 2.4 acres, that's challenging to apply that value to a small block of something. So it's going to be a far more useful tool for larger acreages where you have much larger blocks. They do what's called a subsampling or a resampling, where they essentially use some of the other measurements to divide these large pixels into 9 smaller pixels or smaller areas to match the 30 meter by 30 meter NDVI. That's a little beyond us though, but just keep in mind that the resolution of this measurement is quite coarse. The other issue to keep in mind is that satellites are above the clouds, so they're affected by any cloud cover that will block the measurement. Now, typically in our growing seasons, that is not much of a concern, but here's a measure from June of last year, and you can see at this sample date, there was quite a bit of cloud cover even in the Central Valley. So typically it's not a concern much in California, but it is something, especially in the off season, that we do have to contend with. Now, the other thing to keep in mind is that the satellite doesn't know what's on the ground. We have to interpret that to understand what that satellite reading tells us. So in this example on the upper left, clearly that's nothing but grapevine vegetation, grapevine foliage, which is going to show up in that signal from this block. But in the example on the upper right, you can see now there's not only grapevine foliage, but also quite a bit of cover crop. And in this example, at this time, the cover crop foliage is going to dominate that image by far. So we do have to understand the conditions that we have in place in order to interpret some of that imagery to really understand what it tells us. But conversely, for example, if we get data from those 2 upper blocks or those 2 upper examples, it's easy to tell from the data which one must have a cover crop, just based on our knowledge of what that time of year and what we would be seeing. So if we're trying to predict, for example, or understand when a cover crop was removed, we can easily see that within the data. The 2 pictures on the bottom, which showing the weed coverage here on the lower right picture, those weeds will be visible by the satellite. So they are going to be included in that vegetation index value. So that's something important to keep in mind. That's basically part of our crop that's out in the field. The example on the left, weeds underneath the canopy are not going to be visible to the satellite, so they won't be counted essentially. So we have to remember the satellite is taking imagery from directly above, and it may miss some things that are underneath the canopy. Okay, so with regards to using this to understand irrigation, there's 2 different approaches. One is the NDVI-based approach. So we use the NDVI to calculate a crop coefficient value, the same type of crop coefficient that you're used to, but simply derived from NDVI. And then we multiply that by the reference evapotranspiration to estimate water requirement. The thermal-based approach, we use 1 or more surface energy balance equations to estimate evaporation loss. Okay. So the first approach, the IRRISAT website, is, I think, by far my favorite tool to use for this. Developed in Australia with John Hornbuckle and a group of people. And it's a website that was developed for farmers to use satellite NDVI as an irrigation management tool. And within that website, they then convert the NDVI values to crop coefficient values based on this relationship that I have shown here in this chart down below. So roughly the NDVI is multiplied by about 1.2 to give you the crop coefficient value here. So when you use the website, you'll see the colors in the charts, and I'll show you the KC values. This would be the scale here on the right here. Now, if we were to talk with Larry Williams, or if he's on the call, he's going to tell us that, this is not a true crop coefficient. It doesn't meet the criteria of how a crop coefficient is developed. So when we use this, we should keep in mind that this is an estimate of a crop coefficient from the NDVI, and we use it in the same place in the equation as we would a traditional crop coefficient. But it does have some limitations, or there's some differences between what a true crop coefficient would tell us. And I'll give you an example, though, of how we kind of work around that and use this to our favor. because it does have an awful lot of utility because of its availability for us. So here's an example from that website. So in the Irrisat, you have to create an account, which you can do so just with you need a Google account or a Gmail account. So I went in and I selected this field. Now notice I put in this border outlining the field. I kept a good distance from the actual edges of the field to try to reduce the problems with that edge effect for any large pixels which might overlap the dirt road that surrounds this field. And this is a table grape vineyard in Tulare County, just to give you a perspective here. So when I initially do this, what shows up on the upper left part of the screen is the date. And this is the date that relates to the image that's in this field right now. And I've selected the KC value. So what shows up here is the estimated crop coefficient based on the NDVI. And then the scale is on the right-hand side here. So you can see we're kind of in the orange to yellow period. So fairly small value for this late April of earlier this year. Now, if let me go back one slide here, I forgot to mention. So this date that you see here on the left, this is a pull down menu. So if I was to click on this and pull it down, I can go back 20 years in time and look at values on an 8-day interval. Now, the farther back in time you go, the quality of the data gets worse and worse because the satellite data, the satellite imagery from, let's say, 10 or 15 years ago was not of the same quality as the imagery data that we have now. So it's still, though, a really valuable way. If you're trying to get some historical perspective on what was being done in the field a long time ago, this is a great tool to use to try to understand that. So that is actually one of the ways that I've been using this an awful lot, is just to get a historical perspective on how things have changed in fields over time. Now, if I clicked on that field, it brings up this pair of charts here. So the upper chart shows us for the prior 12 months what the crop coefficient value was over time. That's what those blue circles with the lines connecting them are. And also on that top chart, it gives you a reading of the field visibility. So how clear was the satellite image with respect to clouds? So where it's a clear image, like you see in the summer here, it shows up as a tan background. And if there's any issues of blockage of the visibility, that's what those white kind of icicle looking things are. Those indicate periods of poor visibility. And this program does a pretty good job of removing any data that would come from those poor visibility timeframes, but it's not always perfect. So you can see there's a value here from late September that looks like I would probably have removed that. That clearly is taken during a period of low visibility. But for the most part, the data is pretty darn robust with the measurement. Now, the lower chart, the second chart, is showing you calculated values of evapotranspiration, both as a daily value, that's what the little blue circles are representing, and then a cumulative value over the 12 months. That's what the green shaded area is showing you now. Now, keep in mind, this calculation was made by multiplying the NDVI crop coefficient times the reference evapotranspiration. So there's no inclusion of a deficit irrigation factor. And for that reason, this probably is not accurate for the types of crops that we're growing in California for the most part. So think wine grapes or almonds, any crop where we are using deficit irrigation, this calculation is not going to be accurate. So I would not use this other than just simply as more of a curiosity until they maybe in the future, if this program adds a deficit factor, then we could maybe do some additional calculations with this. But for the time being, let's just look at the crop coefficient value, and you can see the pattern here. So you can actually set this to look at any 12-month period that you wish, and I had now set this to look at the 2020 season. So from January 1st until the end of December. And you see the pattern here. The values are fairly low throughout the winter because there was probably a very limited amount of cover crop or maybe weed growth, just a small amount of vegetation at that time. And then you see the rapid increase around April. and reaches a peak here. Looks like by June, this little dip is an anomaly, probably from the Landsat 7 satellite, stays at a fairly high level throughout the season, and then starts to drop off here. Looks like in August, dropping off before we get to September. Okay, so now we get a feel for what is the pattern throughout the season. And this, to me, is one of the real values, is being able to look at this data back in time and now understand how much vegetation did we have, and then from this crop coefficient value, we can make predictions on how much irrigation would have been required for a site like this. You can also, instead of looking at the data graphically, you can download the raw data. It's just the same data points that are in that chart I just showed you, but just by selecting this data tab here, you can then download as an Excel file and get the same data. So if you want to do some types of further analysis, this is a much easier tool to work with. If you do plan to do this, let me know. I can give you some tips on how to handle the files that you get from this. So here's the basic way that I think we can get the most value from this historical data, which has already been collected for every single one of our farms for the last 20 years, and which we have a very rich data set for about the last 5 or 6 years now with the Sentinel satellites. So if you've been keeping irrigation records in your fields, you can do some really interesting calculations. So we're all used to this very first equation I show you here. Irrigation, so this is how we're calculating how much irrigation to apply. That equals the crop coefficient times the reference evapotranspiration times a deficit factor. So in order to use this equation, we had to have in mind what deficit we plan to apply, and we had to know what our crop coefficient was. If we just simply rearrange this equation, like I have here in the second row, where now we're solving for the deficit factor, if you do this for a year in the past, when you thought your crop, let's say a vineyard, really performed well, and that's what you're trying to duplicate now in the future. If you have records of how much irrigation you applied, let's say on a monthly basis, and then you have this KC value that you get now from this IRRISAT website, you can also calculate the monthly value. And then from IRRISAT or from other weather station sources like CIMMYS, you can get the reference evapotranspiration. If you do this with your past data, you can then solve for the target deficit factor, which you can then use in the future going forward. So if you now solve for this deficit factor for what was a very good year for you at a site, you can now plug this into the top equation and use it like we traditionally do. You now can get the KC value from the NDVI. We have the reference evapotranspiration, and now the deficit factor for your ideal target production. And to me, that is one of the best reasons why you should keep irrigation records in the past, so that you can now do calculations like this, and you have something to base future decisions on, and really compare it to what worked well for you in the past. And so that's kind of my spiel for how we should be using this to try to predict how much we should be irrigating. And this compensates for evapotranspiration conditions, compensates for changes in foliage, because that'll all be based on be reflected in the KC. Now there's a whole nother approach to using the satellite data, and that's just for an imagery analysis tool to see patterns in fields, trends over time that allow us to spot problems. So this is a vineyard in the San Joaquin Valley from last year that in the spring, it had a very large amount of foliage, a good amount of vegetation here. You can see the values here on the KC scale were in the kind of bluish green to blue. So that's a fairly dense canopy. Then by June, that had been reduced quite a bit. So chances are this had been hedged to drop that foliage level down so much. But what you do see are these horizontal bands starting to show up. Now, there are 2 roads that go through this vineyard block. That's these kind of very distinct horizontal bands you see, but there's some other bands that are showing up here. Those to me look like irrigation blocks. This is a fairly large vineyard here. So it looks to me there's some problem perhaps delivering water in this field. And as time goes on, in July, you start seeing more of that pattern. by August, you can see what looks like a vertical area here of higher foliage. That's probably where the irrigation risers are from. And then it looks like water is not able to reach the ends of the fields. So this could, for example, indicate that there's a problem delivering water. Maybe there's a problem pressurizing the system. If I see a pattern like this, I say this is a really good candidate to go out and do an irrigation system evaluation to understand how is water being delivered in this field. There it eventually reaches the full-size canopy. Like in previous years, it just took it a much longer time to get there. So that, to me, is a very clear cause and effect relationship between the cutbacks on post-harvest irrigation that had occurred in the prior 2 years, which eventually led to very weak growth this year. Now, the real positive thing is I think this information was communicated back to the grower, and you can see now the response here this year, post-harvest, that they've maintained that canopy quite a lot. And I wish I had gotten some more recent data here, but when I last downloaded this at the end of October, you can see that even then their canopy was still present. So that, to me, is a really good example of how we can use this historical data to understand what had been happening in fields as a diagnostics tool, but then also as a tool to help us understand what we need to change in our irrigation to help prevent that from going forward. So I'll be very curious to go back and get data from this field next year and see, was this change that was done this year with this later irrigation, is this sufficient now to bring next year's early season growth back to the normal pattern? So we'll have to repeat this.
Mark, we have 5 minutes, Mark.
Okay, thanks, Steve. So, okay, now briefly here, I'll just discuss the thermal method. This is something much more recent for us to do. The OpenET website is our primary tool right now, very recently unveiled. They incorporate 6 different ET models to estimate the evapotranspiration that occurs from a field. The thing to keep in mind is that each of these models can produce a very different value. And so what this website does is that it averages the output of those 6 models as a single ensemble value for that field. The other thing to keep in mind is that this estimate of evapotranspiration includes everything in that field. So soil, weeds, cover crop, that's all part of your crop system, and that's all part of the evapotranspiration estimate. So if you go to the website, this is what it looks like. It's only available for the Western US right now. IRRISAT is global, with the exception of the reference evapotranspiration in that IRRISAT. That's only for a few countries, I think the US and Australia. Otherwise, the IRRISAT NDVI is global, which is one of its big advantages. Here, this OpenET is only available in the Western US. And if you zoom in, what you see in an area is that they've already marked out parcels, which may or may not correspond to the areas that you wish they had marked it out as. And if you don't like it, you can actually draw your own parcels here. But if these do correspond, if you just click on one, it brings up a little chart like you see on the upper right here, where what this shows us is the annual ET, the evapotranspiration for calendar year 2020, and shows you how that varied over that year. Now they have data going back to 2016 in this program. So you can select whichever year you want to look at that data. To get a feel for how these different models can predict ET, I've plotted now the 6 different models independently here on this chart for that same field that I just showed you. And we're looking at data from 2016 up until recently here. You can see the large amount of variability between these different models. So they were all developed under different circumstances, different cropping systems. So there's probably good reason why they may not match exactly our situation of our crops here in California. So what the OpenET system does, its default is just to show us this ensemble average of those 6. And I've plotted the range here as well, that shaded area, so you can kind of get a feel for what the variability in those different models is. So how can we use this as a tool right now? You know, it's a new thing. We're getting the feel for what this actually tells us. I would say right now, just go to the website, observe the data, and compare it to your other irrigation sources. Use this as an additional tool to understand what may be happening in your fields. In some ways, it was really designed more for a larger scale water management, not necessarily to tell you as an individual farmer what's happening precisely in your field. But the data tools in this will eventually be incorporated into tools like Crop Manage. It's a UC program which is designed to help you manage nutrients and irrigation. So that might be the better venue eventually to be able to use that. I think we can expect improvements over time as these models are improved. And I just want to show you this chart here to give you an idea of one of the fundamental challenges of using the satellite thermal data to estimate evapotranspiration. So this is some experimental data that I collected way back in 2004 with some sap flow sensors, and we're looking at patterns of crop transpiration over 3 days. And these are 4 different irrigation treatments in some wine grapes here on the coast. So what I have labeled as 100%, that's just the grower standard, and then there's different percentages based on that. The key thing is here, the satellite passes over once every 8 days in the mid-morning and is passing over for a fraction of a second, taking an image of the thermal conditions. And if you try to kind of look at the patterns here, that mid-morning period is when we have these big spikes in transpiration from these deficit irrigated vines. And you know, that one single measurement time is clearly not capturing all of the variability that occurs within a field like this. So to me, the solution is, if we're going to use satellite thermal data, we need more satellites that pass over at different times of the day to get more data points. I think that's kind of a fundamental thing that we'll need going forward. Okay, and just my final slide here, just to show you where some of this information can be available. The IRRISAT website, and there are some commercial equivalents, you know, I shouldn't say equivalent, but similar providers of NDVI data like OneSoil, the thermal-based irrigation information, the OpenET website here. There are some commercial providers of similar type of data like IrriWatch, for example. Well, thank you very much. I appreciate your attention. And if you have any questions, feel free to contact me later as well. Thank you.
Mark, it looks like we've got one question here. Is the extended foliage coverage of the 2021 growing season going to have an impact on the 2022 spring growth?
Yeah, and that's what I'm hoping happens. I think that extended foliage cover in that example was done on purpose by the grower to have an effect on the 2022 growth, with the idea that they are allowing those vines to accumulate greater content of carbohydrates in the permanent tissues to improve the bud break and early spring growth next year.
Okay. Let's see, one other question. How comfortable are you using IRRISAT data along with soil moisture sensors to monitor irrigation and make irrigation recommendations?
Well, those two things are telling you very different things. So soil moisture monitoring is going to tell you kind of in real time what your soil level, moisture levels are. If you're looking at any satellite imagery for foliage levels, it's telling you kind of what happens, for example, after that time period. If, for example, you stress your crops in certain areas and begin to lose foliage, then you'll see that very clearly with the satellite data. So I wouldn't say those are not complementary in the sense one doesn't replace the other. You would use the satellite data to understand patterns in the field. For example, look at last year's data to see where the heavy foliage areas are versus the light foliage areas to maybe help you identify soil type differences or irrigation delivery differences. And then also use the satellite data to predict how much irrigation you need to apply going forward, and then use the soil moisture data to help verify that.
Okay, very good, Mark. Thank you for joining us and participating in our webinar today.
All right, Steve, thank you.
So we'll continue on with our next speaker, who is Sat Darshan, Assistant Professional Researcher at the Department of Plant Sciences at University of California, Davis. Sat, if you can go ahead and share your screen. He will be talking about uncovering barriers to grower adoption and technical advisor recommendations of nitrogen management practices. Welcome, Sat.
Thank you, everyone, and I appreciate being here today. I will share my screen. Oops. It's a quick preview. Okay. Can I be heard in my screen? Can be seen?
Yes.
Perfect. Okay, I'll get going here. Okay, so thanks, everyone. Again, I'm Sat Darshan Khalsa. I'm in the Department of Plant Sciences. I'm an assistant researcher, training mainly and working mainly with trees and tree agronomy. I had this great opportunity in my postdoc to start working with some great people, Molly and Mark LaBelle, Jess Rudnick, who are all political social scientists on this question about barriers to adoption. And along with Patrick Brown, we have these fine results to share with you today. So thank you all for inviting me here. Oops. Okay. Okay, so just an overview of my presentation. I'll talk about barriers to adoption. What were some of our research goals when we started this project? What was our approach we took? I'll talk about the surveys we collected, what we learned from those surveys, and how really like the farm you're working on really matters within this context. And you'll hear that theme quite a bit, and I'll stress that quite a bit. And for your audience, CCAs, technical advisors, PCAs, et cetera, I think you all know this, but having empirical evidence to just show that this is even more important, I think is super, super critical to communicate with other people. We extended our work from growers to technical advisors, where we asked them similar questions about practices they recommend and what constraints they face. We kind of focused on irrigation. And I'll kind of outline a few other future opportunities of things we're working on in our training and education programs for your audience as well. So for our research goals, we were really trying to understand the link between different adoption rates of practices, farm characteristics, and some of those challenges associated with the practices. I use these pictures here to show that we were asking about nutrient budgeting, basing on knowing what crop we're growing, some of the irrigation practices, soil health practices, as well as some monitoring practices, like here, sampling soil for sampling the soil for different characteristics. We also want to then identify key motivations for those growers and technical advisors, and ultimately for growers, who are the information sources they're turning to for these types of conservation practices. And lastly, we wanted to uncover the constraints of the PCA CCA as the main information source. So spoiler alert, growers identified the CCA and PCA as the main person they turn to for information. So we also wanted to understand what constraints you all have when it comes to sharing your expertise and advice with growers. So we did surveys with CCA and PCAs as well. So our overall general approach is that for growers, we did a number of mail surveys and in-person surveys. This was both in the Sacramento and San Joaquin Valleys. And then earlier this year, we launched an online survey where we targeted CAPCA membership and Western Region CCA membership. This was statewide, where we got over 500 of you all who filled out the survey. So thank you if you did participate. We certainly appreciate it. Some of the statistics I'm going to show, I'll show some just descriptive statistics, which are just average effects, like out of the population who responded, what was the average effect and how did that differ between different groups, using some p-value comparisons, but also show what's called logistic regressions, which is slightly different. What it does is it actually shows the probability that if someone has some sort of characteristic, what was the probability of them increasing or decreasing adoption of that particular practice. So that's really key because it has to do with actually probabilities of if you identify this characteristic over that characteristic, what is the probability that you're going to adopt the practice? So I'll show both of those. So I just want to give an overview of some of the numbers I'll be presenting. So this is just average results. Basically, we asked about these suites of practices. So the green ones we call like fertilizer use management. The blue ones are more centered around irrigation. And then the ones at the bottom had to do with soil health. And overall, the fertilizer practices did dominate. They were at the highest adoption rates. And often because there's also some co-occurrence between them. Like if you're doing leaf sampling, you're probably doing some soil sampling too. So we kind of deduced that a little bit from these results. But when it came to irrigation and soil health, those practices were all secondary to the fertilizer practices. And there could be some explanation why, but maybe just because they're not just inherently linked with fertilizer use, even though they do affect nitrogen management, et cetera. So that could be some reasons. Other reasons could be just about the technicalities and other challenges associated with them. And I'll have some data on that to explain a little more. What we did show is this idea about co-occurrence, and this is a separate paper where we asked in green fertilizer practices, blue irrigation, and we had cover crops as the one soil health practice. And basically what you see is the nodes are essentially the adoption rates, and then the weight of the line connecting the nodes has to do with the probability that they're likely going to happen on the same farm. And what you can see with a lot of these fertilizer practices is there's lots of co-occurrence, right? If you're doing split application, you're highly likely doing leaf testing, and you're also highly likely doing soil testing, and also with soil and leaf testing. So this was just like a graphical statistical way from the data to show this. However, when it came to some of the other practices, they were sort of lower adopted, but also less related to them. So the one for irrigation was the moisture probe. It was most correlated to some of the fertilizer practices, but interestingly enough, not so related to the other irrigation practices. And then cover crops was kind of a bit of an outlier, had low adoption and very low co-occurrence with other practices. We also, this is the same graph I'm showing here, but I'm sort of revealing the statistics. We asked growers about if they farmed the parcel that they were farming was a nut crop like almond, walnut, pistachio, or a fruit crop, which is a lot more diverse. Could be stone, citrus, or grapes. And what we saw there is that, when it came to some of these fertilizer practices, the nut crops were significantly greater than fruit crops, as well as the use of a pressure chamber, which we thought was a little surprising, but could be explained that in general, the nut crops are using and demanding essentially more fertilizer and water than many of the fruit crops are. And so maybe there is more of a conservation incentive there for some of these nut growers. Another reason could be is that almonds, for example, have been a large focus of research of the last decade, and maybe a lot of that fresh information for almonds is being readily adopted, and people are trying some of these things out. Fruit crops, of course, there's a lot of progress done, but because of the diversity, focus on quality and other aspects, it's not so easy to do research in citrus and easily translate it to stone fruits, for example. So for those reasons, each of these fruit crops need their own investments in research to really hammer out these practices. And that could be a possible explanation of why we saw lower adoption. Another possible explanation for lower adoption was that the fruit growers in general identified more challenges, and challenges associated with all the practices. So in this table, we see those practices listed, and then we asked across the board, again, general statistics here, what percentage of the growers reported levels of uncertainty with the practice, the need for technical expertise as a challenge associated with that practice, and lastly, is there a challenge associated with this practice being effective, so efficacy? And across the board, what we saw was that indeed fruit growers did identify more challenges than nut growers, and in a lot of cases, it was significantly greater. So we sort of thought that was one explanation, and that could be because of just less research available for fruit growers or other reasons. But we also found out that when we asked them about what information sources they used, of course, we see the PCA right here in the middle, CCA being less, but let's keep in mind here that many of the growers we survey, probably you might be a CCA and a PCA and they just think of you as a PCA. But when it comes to the technical advisors and UC being important information sources for growers, but again here, for those information sources, including grower peers, fruit growers identified significantly less than nut growers. So not only are fruit growers experiencing more challenges with these practices, they're also identifying fewer information sources. So they have sort of less resources and knowledge available to them to adopt those practices. So let's move on a little bit more about in general findings that we've found that had to do with how farms really matter. And this, what I'm showing now is what were the results of those logistic regressions called marginal effects. So 0 essentially means that there was no effect of the parameter on adoption, and positive means it was a positive effect on adoption, and negative would be a negative adoption. So for this parameter, we're looking at parcel size, and we're going to assume the baseline is a parcel that's 50 acres, but anyone who identified a parcel that had more than 50 acres, that increased the probability across the board for all the practices and quite a bit more for some of the irrigation practices. So indeed, this is not a finding that isn't known in the literature or in general, but what we do know that parcel sizes, larger farms in general have more resources, less risk associated with trying new practices. And indeed, we found that was the effect for all these different practices. So larger parcels, larger farms increase the probability of adoption of all the conservation practices we surveyed. But what we found that was also very interesting is that irrigation systems had an effect. When the grower, in this case, it says micro irrigation. So what that means is the baseline was the farm only had flood irrigation or some sort of surface border check irrigation in place. And when the growers identified using micro irrigation for that parcel, many of those practices had a positive effect on adoption. So just by switching to micro irrigation, we saw a greater adoption of many practices. But again, not for the soil health practices. There was no effect with these two, and cover crops actually had a negative effect. What we found that was actually even more interesting related to water and farms and the farm infrastructure is when we asked growers what the water source is like on that farm. Again, in this case, the baseline for the grower would be groundwater only, compared to growers who identified having both surface and groundwater access, meaning that particular parcel had the ability to draw water from ditch water or also had a well on the property to get groundwater. And we kind of thought of that as a kind of a proxy for water security. In those cases, indeed, we saw positive effects on adoption for all practices when it came to growers that had more water security. And that could very well be if you have, greater water security, you have more time and resources to focus on other parts of farming that have those particular parcels. So we found that to be a unique finding. Let me move on to the technical advisors, just keeping an eye on time. So we asked the same type of questions. What types of practices do you recommend to your growers? So this is the same type of question we asked the growers, but we're turning around and talking to CCAs and PCAs and saying, hey, what types of practices are you recommending? And what we found that was actually quite interesting is that it was very similar to grower adoption. So many of the practices that CCAs and PCAs are talking about with their growers are indeed similar to the practices that are actually being adopted. So we see some of these fertilizer practices here on top, followed by some of the irrigation, and then fewer lower discussion around some of the soil health and other practices. And we felt that was just really just grounded in the knowledge base that many of the growers are accessing similar knowledge, this technical advisors, and it looks like there's a clear communication line between the two. But when we asked them, about perceived challenges, that we actually got a little bit of a different response. We asked technical advisors, what do you think growers are perceiving the challenges associated with some of the crops and, some of the practices, I apologize. And what we thought there was we saw some different results here is that some of these soil health practices here on the top, we're looking at organic amendments and cover crops. They had lower amounts of technical knowledge, practice of efficacy, and uncertainty. So this is the blue orange and gray respectively, and greater amounts of responses about challenges about costs and labor and supplies. So what we saw with soil health is that the adoption were low, but often it's being perceived as something that has to do with cost and labor and supplies rather than it's really being a technical issue that needs to be worked out with potentially more research. That's not to say that we still need to do more in that area of soil health, but maybe in communicating greater about what is the actual economic benefits of doing it, not just some of the other parameters that growers might not be important to growers. But what we did see is some of the other practices, as I alluded to, have more technical challenges, and specifically when it comes to the nitrogen budget and the irrigation practices. So in those areas, we see that there's a larger dominant response here for technical knowledge, efficacy, and uncertainty. So just keeping in mind that there is this balance between different types of practices about what's the perception of the challenge associated with them. Some of them have to do more with technical, technical knowledge type questions and issues that need to be worked out. And some of them could be more tangible, like it's an economic issue. And so teasing those out for us was a good lesson learned. Last, I want to touch on this idea of irrigation constraints, because we saw a lot of opportunities where we did some focus groups and we were asking about these questions. And one of the questions right off the bat is like, well, if you have an irrigation, if you're a CCA and you're developing a nitrogen budget and recommending the best fertilizer practices, but then you just sort of have no input or say over irrigation, do you think irrigation practices are going to affect your nitrogen budget? So this was kind of a softball question, of which 97% of CCA technical advisors said they did. So this is not a surprising thing, but what we saw there is that there might be some disconnects between how water is being managed and how fertilizer is actually being managed. But indeed, the technical advisors are fully aware that you can write up a nitrogen budget, but if the grower is going to manage irrigation in a way that's maybe not the best for that particular crop or parcel, that it's really going to affect the nitrogen budget. So that was kind of a finding that we had expected to see. We also had this question, maybe PCAs and CCAs just don't feel like they have enough expertise to talk about irrigation with growers. Indeed, but that was not the case. In fact, though they had greater levels of rating of their expertise as medium and high for nitrogen management, it was actually equally or almost equally as high for irrigation management, but slightly lower. But indeed, so we don't think that the PCA, CCA individuals are not experts enough to be able to discuss irrigation with their growers. So the last question we asked are, what are the barriers to advising on irrigation? And this is where it really sort of came to light for us, is that, yes, there are some people that talk about time and labor, right? You're not really being paid for it. Maybe some lack of knowledge. It's not really part of my role. There could be some liability associated. But bar none, 50% of it was just, there's this lack of control over growers and how the growers are willing to manage their irrigation water. So this was a really interesting take-home message for us, because it made us realize that there's so much work we can do around nitrogen management, promoting good practices around nitrogen use efficiency, monitoring, building nitrogen budgets, but without bringing in that irrigation piece, there's only just so far we can get in terms of really just improving improving practices and making sure we're being protective of our water and other resources. And so we turned to technical advisors, and really this was an important take-home message for us for this project. I just want to highlight that we do offer CCAs a nitrogen training course where we do talk about all aspects of nitrogen, including irrigation. This is an online course that's available for continuing education units. You can go to this website, ucanr.edu/nitrogen course. The course did start last month and will run until the end of the end of December, essentially. But it is a asynchronous course, and then you can take it as you go. And then in January, I'll be hosting some discussion sections to sort of kind of bring together some of the concepts that are taught in the different modules. Pretty much everyone's given us really good feedback on the course. So if you haven't taken it or are looking for CEUs, it's a great opportunity. It's tailored to the CCA level, right? So anyone on this call would probably really enjoy its content, but it is open to anyone. So anyone who is interested in learning about nitrogen management, specific to California, irrigated lands especially, this is a good course to you. We even open it up for growers who are looking to take the grower's self-certification. They can actually take this course to fulfill that requirement. So that is something that we're offering now. And then also we have this nitrogen specialty that's offered by the American Society of Agronomy. This is essentially by earning this specialty, you have fulfilled the regulatory requirement that you can then fill out the irrigated and nitrogen management plans per the state irrigated lands program regulations. So if you are a CCA and you do not yet have that nitrogen specialty, you can take this exam and upon passing it, earn that specialty. Just keep in mind that the course and the exam are offered in tandem. So if you take the course, it really prepares you for the exam. So the next exam will be held in the first week of February of next year. And then I believe it's also going to be held in August in summer as well. So just some quick take-home messages. I wrap up here. Barriers to adoption. We've had some recent advances. We know that a lot of the approaches we're doing are actually working. The research we're doing, the extension models we're following, these seem to be working because we're seeing uptake in a lot of these practices that we'd like to see. But there's definitely still room to be, some more work to be done around irrigation, around soil health, and other types of practices. Not to say that they're all perfect for every grower context, but there is certainly opportunities to talk about this more with our growers. The grower surveys really show that the farming context is really important, but at the end of the day, we need to still convey that growers need the freedom and they just need awareness about these different types of practices, because really they have to make it fit for themselves. So as long as we're continuing to advocate for that, using education, extension, other types of approaches, I think we're going to continue on the right path. When it comes to technical advisors, I think this model that we're taking of not just teaching growers, but also teaching technical advisors to be the teachers, right? So teach the teacher is important, and I think we're making progress in that area as well. But we also know that there are certain limitations out there, and I talked a bit about irrigation. There's only so much we can do if major parts of a system are just sort of outside of control. And that's not to say that we need to start telling growers how to irrigate, but at least we can start having those conversations to maybe get us, to improve a NUE of a particular parcel by 5 or 10%, because that can go a long way. Lastly, there are some future opportunities. We know that education is really key, and then we have some more other sort of proven outcomes from this work that we'd like to continue and extend to talk to others. So I certainly want to acknowledge all the Water Quality Coalition and MPEP leadership that really helped us with this work, and also the leadership at CAPCA at the Western Region CCA, and of course to the CDFA FREP program for funding this research. So thank you, everyone, and I think I have a few more minutes for questions.
Zach, thank you for that presentation. It looks like we've got a question here. Which of the challenges is the easiest to overcome in the adoption?
Yeah, so I think the way I would answer that is depends on the practice. So I think at times, if we're talking about some of the soil health, let's use compost. I do lots of, some research in compost and almonds. A lot of times it's not a technical issue, right? You got a spreader, you got some compost, putting out in the orchard's not too hard, right? But often it's like looking at the cost of trucking and the compost, and maybe you have to rent a spreader, and penciling that out and trying to find the ROI, right? And well, the ROI on that's probably not going to come for a couple years, if not 5 years. It's not going to come by boosting your yield the next year. Research shows that. So that's a big challenge for the adoption of organic amendments, for example, is just recognizing how to balance those costs and when to expect a return on that investment. On the other hand, when it comes to scheduling ET, and I think the previous Mark was talking about that, there's some technical aspects around getting accurate measurements for evapotranspiration and then translating that information using crop coefficients and other types of information to an effective irrigation schedule. So that could be a challenge that could be easily overcome. However, you're probably going to need some technical assistance to do that if you're not necessarily a real data savvy grower, for example. So I think I guess my answer to that question is really depends on the practice, but being aware of what those are is really important, because I think you can overcome the hurdle faster that way.
Yeah. Sat, the last data slide that you showed was on irrigation and growers not kind of giving up control for one reason or another. Some of those growers, let me just eliminate this and take a look at your slide. So yeah, some of those growers are small growers, and you know, they're doing everything themselves, whether it's 10 acres or 20 acres or something small that maybe doesn't, they can't afford a technical advisor or the cost that goes along with all that other stuff. How do we reach and train those growers? How do we change that? Some of those bad habits that growers have because they just don't have the technical expertise.
Yeah, I mean, I wish, you know, I recognize that agriculture is a private enterprise, right? I'm doing my work here at the University of California, but I work in business too, and I recognize it's a private enterprise, right? So growers got to see some value and paying for a product or service that's going to return on that investment. And technical advisor like the CCA, it's the same thing. You're getting paid for your time, and or you're getting some sort of royalty from product sales, for example. So I think the answer to that question is simply, I mean, the simple answer, which may not be practical, is that providing grower with more technical assistance around irrigation. And what are some good practices around irrigation, talking about distribution uniformity, for example, or scheduling irrigation with ET, but also, you know, soil moisture sensors, so you kind of know, you know, at what depth is your wetting front moving to, and bringing that awareness to growers is really critical. But, you know, all those don't happen by themselves. They kind of have to happen in unison. So I think that's going to require more investment, but that investment is probably going to have to come from the public sector. And if we as a public want to see that water is used more efficiently, and we're interested in water quality, then I think we need to invest in the ability to do so. So I'm really open vocally about this idea of conservation entrepreneurship. Why is it that we can't set up a grant program from the state of California that pays CCAs to go out and talk to small growers about irrigation, right? The grower can't necessarily pay for it right away. The CCA is not going to do it for free. But if we have an interest as a public, and I'm talking about you, me, and everyone on water, and why don't we just incentivize the CCA to go out and have that conversation, and make sure we have the right checks and balances in place to make sure those communications are happening. So I think we can go a long way. And so UC can do so much, but I'm not proposing we need to create a whole new branch of the government to do this work. I think CCAs are clearly on the boots on the ground, along with PCAs with those growers. And if we can incentivize them to have that conversation, I think there's a lot that can be done. So I feel like growers are amendable. All the growers I talk with are always interested in trying to do more or better, or however it needs to be done. But we need to have the right incentives in place to do so.
Sat, I like that idea. And if there's anything that Sun-Maid can do as a, you know, to write a letter or support of any other kind, I'd be happy to have that conversation with you, because I think that's a great idea for reaching some of these small growers. I think this last summer was really a summer where we saw irrigation mattered, you know, especially doing it correctly. And when you didn't, there was, you know, consequences for that. And so I like your idea. And we're happy to help and support that.
Great, thank you so much.
Sat, thank you for coming and joining us today. We appreciate your presentation, and we look forward to seeing you again.
Okay, thanks everyone.
So we'll move to our last speaker. Our last speaker is Maria Zemkeller. She's a graduate student in the Department of Horticulture and Agronomy at UC Davis. And Maria, if you can share your slides. She's going to be covering cover crops and tillage effects on grapevine physiology and metabolism in a mature vineyard in the San Joaquin Valley. So Maria, it's all yours.
All right, can everybody see and hear me all right?
Yes.
Perfect. So like you just said, Steve, I'm a master's student at UC Davis in the Horticulture and Agronomy graduate group, and I'll be presenting on a current project from the Curterell Lab called Cover Crops and Tillage Effects on grapevine physiology and metabolism in a mature vineyard in the San Joaquin Valley. So I'm first going to give a bit of background on the different cover cropping systems available in California, and then I'll discuss an applied trial that we're finishing up in Fresno County and a sister study being conducted in Napa County at the Oakville Research Station. So I think the best way to approach the topic of cover cropping is to look at it as just another tool in the tool belt that can then have these trickle down effects. And some of those main effects that we see are improvement to soil structure, mitigation of soil erosion, improvement of soil fertility by way of improving soil microbial diversity, because that's really what's doing the work under the soil, as well as frost protection and encouraging beneficial insects, depending on the types of cover crops being used. But all of these benefits really do depend on a number of factors, and they're very site specific. So some time should be spent determining the right cover crop for the particular site that you're planting on. And these are determined by soil characteristics, vigor of the site, and your corresponding objectives, whether you're trying to devigor or improve vigor of the vines themselves. Cultivar and rootstock are particularly important there. And pest management, including weed control, whether that's vertebrae or other insects. And then the most important guiding factor here would be water availability. So at the most broad level, we can kind of split cover crops into two categories, annual species and perennial species, and then again separate those into till and no-till systems. Although there's a fair amount of gray area in separating them like this, whether you're planting cover crops in every other row, you're using a no-till seeder, or you're cultivating prior to seeding the cover crop. But for the purposes of this experiment that I'll present on, I'm just going to discuss them within these two categories. So a majority of cover crops in California vineyards tend to be annual grasses used under the till system. However, there's a number of annual cover crop species available, both those that reseed, like clovers, brome grasses, and those that don't, like barley and oats. And those can be used under both no-till and till systems. But the perennial species, including fescue and turf grasses, are really optimized under no-till system, and they're able to really enhance the structure by way of binding the soil together with these dense fibrous roots and the accompanying root exudates. So most grasses are generally believed to be devigorating, although turf and fescue grasses more moderately so. So we decided to conduct an experiment in Napa and Fresno County using a perennial POA hybrid species to really tease apart how using different cover crops may influence the grapevine physiology itself, and then its influences on soil dynamics. And I'll get into that after a little bit of more background. So the San Joaquin Valley is one of the leading irrigated viticulture regions in the world. However, decreases in precipitation amounts and increases in temperature as a result of climate change are threatening soil water content. And we're also seeing more unpredictable rain events, which can induce spikes in nitrous oxide emissions, which is a greenhouse gas about 300 times more potent than carbon dioxide. So cover cropping is generally regarded as a promising or sustainable tool to reduce soil erosion and water loss, while also improving soil organic carbon at the surface and in some instances deeply. But there's a lack of information on how these cover crop systems work with different tillage systems in California vineyards, and then their influence on plant physiology and soil dynamics, including greenhouse gas emissions. And you can see in the figure on the right that cover cropping is a pretty dynamic process, not only just choosing the cover crop for your site, but you also have quite a few carbon inputs coming into the system and outputs. So the carbon inputs from the target crop or the crop itself, the cover crop, those root exudates, as well as the carbon that they're enhancing in the soil. But then you also have losses just through soil respiration, cover crop respiration, and then if you're in a till system, the tillage itself. So the purpose of this study that we conducted was to find the best management practices of the vineyard floor using different cover crop and tillage systems to preserve plant available water prior to the start of irrigation. So we took a systems approach to understand how well some of these practices regarded as sustainable, like cover cropping and no-till, may mitigate greenhouse gas emissions and their combined effect on grapevine physiology. And we also hope to give a recommendation to growers regarding the utility of a novel low-stature permanent grass, which is that POA hybrid species that I mentioned. You can see on the left here. So we wanted to be able to see how well that works in San Joaquin Valley vineyards. So we conducted a 3x2 factorial design study in Fresno, California with 3 cover crops, including a perennial grass, which was a POA babosa hybrid, annual grass, which was barley, and then resident vegetation, so just natural weeds, under both till and no-till systems And you can see that treatment structure on the right, that table on the right, 6 total treatments. And this was on a Ruby Cabernet vineyard on Freedom rootstock, typical vine and row spacing for the production region, and it was drip irrigated. And we drilled the cover crop according to the seed manufacturer's best practices, both for the POA species and the barley. And that was done in 2019 and 2020. So we're now finishing up the second year of this project. So some of the parameters that we measured in the plant itself, we looked at plant water status, leaf gas exchange, carbon assimilation of both the grapevine and the cover crop, as well as dormant starches and sugars and harvest components, really looking at yield and all of that that encompasses. We also looked at total soluble solids, titratable acidity and pH of the berries. And then within the soil, we measured soil electrical conductivity at 2 depths, a shallow from 0 to 0.75 meters, and then a deep from 0.75 to 1.5 meters. We measured total organic carbon at 2 depths, 0 to 15 centimeters and 15 to 30 centimeters, as well as soil respiration and greenhouse gas emissions of the primary biogenic gases, methane, carbon dioxide, and nitrous oxide, using the static chamber method from the USDA, which is shown in the top right. You'll have to excuse me, I'm getting over a cold, so my voice may go in and out, but I'm trying my best. So what we saw in 2020, and most of the 2021 results I have here besides our soil data, this is leaf water potential over the 2020 season, where the perennial grass under both till and no-till settings, which is the green and yellow, increased plant water status by about 30% early in the season, just before the start of irrigation. And it actually allowed this particular cultivator to delay that first irrigation set. However, it didn't hold throughout the season. And overall, we saw no differences between tillage system, nor a statistical interaction between the cover crop and tillage system itself. And you can see in that chart on the right-hand side where we saw significances. And definitely between date, which is just a matter of weather. In 2021, we had another especially dry year, and not surprisingly, leaf water potential reflected this. We didn't see any differences in water status between cover crop or tillage, just among the dates of measurement. We did see a 10% increase in plant water status among the perennial grass, but this was not statistically significant and it didn't hold throughout the season. Likewise, we saw no differences between cover crop, tillage, or an interaction amongst tomato conductants. However, there was a difference between dates, like we saw in leaf water potential. Again, just a matter of weather. And you can see in the figure on the left, stomatal conductance over the season, represented by a line graph, and then on the right, perennial grass did appear to show an increase. However, statistically, this did not hold. And in 2021, we saw the same thing. Again, no differences between cover crop or tillage system, but this could suggest that implementing a perennial grass cover crop, or even switching from till to no-till settings, has little effect on grapevine physiology, but could improve early season plant water status in the San Joaquin Valley. So to look at that even further, we calculated water footprint, which is defined as the volume of irrigation water used per unit yield produced. And it's a useful indicator of total water used for production. And we estimated this as the sum of 3 components: blue water, gray water, and green water, and then the total. And we calculated that for not only the grapevines, but again, took a systems approach to this study and added in the cover crop as well. So what you see is the combination of the cover crop and the grapevine itself. And we saw no effect of tillage or cover crop system, but the similarity of the cover crop water footprint, which is not shown here since this is the vineyard, but the cover crop itself did not vary much, which I think is particularly important here, because despite the cover crop having very different growth habits, that POA being really low to the ground, a lot less biomass, whereas the barley is producing a lot more biomass, very high stature, we didn't see any additional water being required or an influence on the vine itself. And in 2021, we again saw no differences among water footprint of the vineyard nor its components. In 2020, we also saw no changes to yield or yield components when we looked at berry weight, degrees Brix, total sugars, pH, TA, anthocyanins, or yield. And this may again indicate that a new cover crop like this low stature permanent grass, or perhaps implementing a no-till system, can be put in irrigated vineyards with no effect on production, but still improving early season water status. We did, however, see some differences in 2021 among TA, anthocyanins, and degrees Brix, where there was a year-to-year difference among all three of these, and then an effect of tillage on titratable acidity. But the year-to-year difference can easily be attributed to just a function of harvest time, since this year we ended up harvesting the crop almost 4 weeks early. So the degrees Brix is just a reflection of that early harvest time. But the impact of tillage, I think, is pretty interesting, and maybe may indicate that those vines under tillage didn't ripen as fast, although we didn't see that reflected in Brix, but it's still something worth exploring. And hopefully another year of data could show us what that may be caused by. We didn't see any differences in fructose or glucose when measured in dormant wood. So we looked at starches and sugars at pruning, and this was for 2020. We haven't yet collected 2021. However, tillage did have an effect on raffinose content, which was higher under the till setting compared to the no-till. And this decrease in raffinose content under no-till may indicate a lower degree of stress going into dormancy. And we're hoping to see that reflected in 2021 pruning weights as well. So within the soil physiochemical parameters that we measured, we saw no changes to soil pH, although we did see total organic carbon differ among depth and tillage levels, was what we expected. Mid-row EC was measured in mid-January, as well as deep EC, and we did see a depth effect there as well, though not among tillage. And soil EC has actually shown to be an indicator of plant available water. So this is total organic carbon by depth. And you can see here that in the upper 15 centimeters of the soil, there's actually about a 30% increase of total organic carbon compared to the 15 to 30 centimeters depth. And this is just reflective of literature, but it's nice to see that corroborated at this site, because this site is particularly sandy. This is total organic carbon by tillage, where we also saw a difference, an increase of about 18% total organic carbon among no-till than till. And literature is, there's quite a bit of gray area between total organic carbon looking at separation by tillage, and very site specific depending on soils and weather conditions. But it was interesting to see this even in a pretty arid climate. And this is soil apparent electrical conductivity by depth, which was exactly what we expected to see, quite a bit more water, indirectly measured water in the deeper 0.75 to 1.5 layer compared to the shallow. So we also measured and calculated the net carbon of the vineyard system, again, being the grapevine and the cover crop. And when we extrapolated this to a hectare scale, we saw a clear separation between tillage systems, although not within the cover crops, where we saw a higher total net carbon value under no-till compared to till. And these values were relatively in line with current literature, although slightly under, again, probably a function of this just being a really arid climate and pretty sandy soils. We also measured greenhouse gas emissions of methane, carbon dioxide, and nitrous oxide for one full season. We're currently in the midst of collecting the second season to capture the past rainfall and hopefully some more rain next month. So emissions were monitored for all three gases at 4 time points, which was 0, 10, 20, and 30 minutes, using that USDA static chamber method I pointed out earlier. And we measured all 6 treatments pre-till, and then again post-till, although clearly the no-till treatments were not cultivated. We just wanted to establish a baseline for statistical analysis. And before tillage was conducted, we did see differences between carbon dioxide and nitrous oxide. And then after till, that still held, as well as an effect of tillage on all 3 gases. which is also corroborated by an interaction between cover crop and till itself. And that you can see that in the fourth category down under post-till. So clearly carbon dioxide was a lot more influenced by the cover crops that we were looking at. So when we look at the numbers of the values themselves here in parts per million, you can see that the annual grass under tillage exhibited the highest carbon dioxide emissions in contrast to the lowest value, which was the no-till perennial grass. And again, under carbon dioxide, we did see an effect of cover crop as well as that interaction between cover crop and tillage. So we're hoping to see similar results in this next season. Some previous research conducted looking at nitrous oxide emissions in comparison to different cover cropping systems in the Lodi region has shown that cover crops have really minimal influence on the nitrous oxide and all three primary biogenic gases. So it's really interesting to see that carbon dioxide jumped out here, although I think it might just be a function of soil or of respiration of the cover crop and the biomass there. So the last component of this project is an economic analysis, where we use annual cultural costs to calculate and compare those across the season per treatment. And as mentioned, there's a sister study conducted in Oakville, which is a very different economic climate. So we calculated those costs separately for Napa County as well. So in Napa, we found that transitioning from tillage with resident vegetation or an annual grass to a perennial grass under no-till could save between 3 to 6% of annual cultural costs, which works out to about $300 to $550 per acre, respectively. And then in Fresno, that transition would save between 9 to 16% of annual cultural costs, so about $175 to $350. And we calculated that the return on investment implementation of this particular cover crop would be about 1 to 3 years. So in conclusion, we saw that perennial grass we looked at resulted in a 30% increase in midday leaf water potential. And we saw that in early spring of 2020, but only a 10% increase the following year. However, when we extrapolated values to a hectare scale, we saw that the perennial grass cover crop demonstrated a decrease in soil respiration, which is one of the primary sources of carbon loss in agricultural soils. So consequently, the net carbon assimilation of the system with perennial grass under no-till was enhanced compared to that with the barley or the natural vegetation. And at harvest, we saw no changes to berry mass, pH, acidity, or sugar in 2020. However, we did see an effect of Brix, TA, and anthocyanins in 2021, though this is largely attributed to just timing of harvest. So we can conclude that the use of cover crops under no-till systems could possibly be implemented in irrigated vineyards of the San Joaquin Valley with little to no effect on grape productivity, but improving early season grapevine water use. So a couple remaining components for this study are to include greenhouse gas flux calculations for the second season, as well as characterization of the bacterial and fungal communities by fungal groups. So we're hoping to put together something like you can see on the left there to really tease apart what bacterial and fungal communities are working to alter greenhouse gas emissions, any changes that we saw there, and then still collecting our final soil samples to look at how total organic carbon changed over the course of those full 2 years. Yeah, so thank you to my lab for all this work, and that's all I've got.
Maria, thank you for that presentation. Couple of questions. What's the approach to going from native vegetation to a perennial grass? And what's the preparation? And then in terms of water to get it established and then use over the season?
Yeah, so for this particular experiment, we did cultivate prior to seeding that cover crop in 2019. Because we had the no-till and till settings, we did have that first initial cultivation. And then this particular cover crop should reseed. However, we did not have good rains in 2019, so we ended up reseeding again just without cultivating. But for what this particular company recommends, you would just cultivate, seed, and then you shouldn't have to reseed again. Although we saw rains kind of heavily influence that. And then we did not irrigate that cover crop at all in these 2 seasons. But I do believe that my lab will be continuing this project. I'll be graduating pretty soon. But they're going to continue to look at how using winery wastewater to irrigate can influence the growth and look at the same things just with that additional irrigation.
Okay. And then you said the vineyard that you used was a pretty sandy soil. How dense was that cover crop when you established it on that sandy soil?
Yeah, actually the photo that I first showed, this is the stand of 2020. So we had better stand in 2020 than we did 2019.
Okay.
But this is about what we ended up with. And then it goes dormant probably early summer. That ended up being end of May, early June in Fresno, and then a bit later in Napa County.
Okay. And then final question here, what would be your recommendations to a grower who hasn't used cover crop? I think we just saw SAT's information, one of the lowest things was adoption of cover crops.
Yeah.
So what would be your recommendation for a grower, or how would you encourage them to use cover crops and gain the benefits?
Yeah, I mean, as I outlined in the beginning with my cover crop background, using cover crops or the species that you're using and the system itself, it really does depend on site characteristics. So I think starting with just an assessment of the soils that you're on, the vigor of the vines, looking at this is probably more common up north than it is down south, but if you're trying to devigorate a site or improve vigor, just looking at what your goals are. If you know you've got a particular like vole problem or vertebrae problem, maybe an annual grass or a brome is not going to be the best. You're just encouraging habitats. So we're just looking at a lot of the pests and disease pressures that you face, as well as site characteristics. I think there's a lot of great resources out there to pick species, cover crop species based on your goals.
Okay, very good. Thank you, Maria, for presenting today. We appreciate you coming and sharing with us
Thank
today
you
at
for the
Western
invitation.
Region CCA. You bet. So with that, we are finished. The speaker information is in the chat feature, so you can take a look at it there. There's also the QR code there that you can scan to get your CE units. We'd appreciate you giving us some feedback on these webinars. So I think if you go to the website or to the email that you received, you can send us feedback and perhaps some additional topics that maybe you'd like to see in the future. I think there's going to be a link to the recordings of today's webinar that you can access for review. Miranda, is there anything else?
Nope, that sounds good. And as Steve mentioned, we are not collecting the presentations from our presenters and distributing them. So if anyone would like to revisit any of the material, they can email Madeline at wrcca@calagjobs.com, and we can get you a link to the recording to review any of the presentations today. But we aren't actually going to be providing PDFs of the PowerPoints to individuals.
Yeah, I think with the contact information, you can contact those speakers at any of the webinars and ask them for a PDF of their presentation if they're willing to do that. Sometimes they have data in there that hasn't been published yet, and they will not give out their presentation until the data has been published.
So at this point, that concludes the webinar. What we normally do is we go ahead and we leave this last slide up for another like 5 to 10 minutes, and then we'll shut it down, just so everyone has a chance to open up their CCA app and scan the QR code through the app. And then if you don't have the app and you don't use the QR code system, you'll just have to wait what ends up happening is we have to export the Zoom attendee list and then provide that to the international CCA office, and then they go through and audit it. It can take a couple of months before your CEUs get put into your account, but it will be done.
Miranda and Madeline, thanks for putting this together. Great job, and looking forward to December 14th for the next webinar.
Yes, everyone. Thank you for your time, and we hope to see you at the next one.
Very good. Thank you.